Welcome friends. Today we are going to learn about the stability of control systems. As we have studied different topics to understand how a control system behaves or what are its specific parameters in time domain and frequency domain, all this information is required to understand how a control system will behave stably under certain situations. So these situations could be the parameter variations of the system or the different inputs to the system which are external. So let us see the points we are going to discuss today. The points we will discuss today are the concept of stability, asymptotic stability, absolute stability, conditional stability, and some related concepts. So when we speak about the stability of a system, we should know that stability in a system implies that changes in system inputs or initial conditions or system parameters do not result in large or big changes in the system outputs. So let me write this statement for you. So we start with stability. So stability in a system. Stability in a system implies that small changes in number one, the system input, the system input. Number second, initial conditions. Number third, the system parameters. Any such changes do not result in large changes in system and output. So large changes in system output. So again, I would like to mention here that stability is a characteristic of transient performance of the system in most of the cases. So generally stability is a characteristic of transient performance of a system and we will relate it mostly to the relative stability of the system. Relative stability of the system, while if I speak about the system when the system has reached the steady state, so while on the other hand the stability study in steady state will relate to absolute stability. Absolute stability. We will see this in detail after some time. So we can take a closed loop system, closed loop control system that performs stably with specified boundaries of parameter variations. So that is the requirement, because whenever we are considering or declaring about the stability of the system, we are very much concerned about certain parameters of the system. So the stability of the system is always verified in terms of certain parameters. So let me write this as statement: a closed loop control system performs stably with the specified boundaries of parameter variation. So when we speak about a linear time invariant system, which is actually the system of our study in our context, this model is stable provided the certain conditions are satisfied. So for that we will study the asymptotic stability criteria. So let us go for it. I write here asymptotic stability criteria. So we'll see a linear time invariant system, that is LTI system model is stable provided the following two conditions are satisfied. So what are those two conditions? So the condition number one is when the system is getting a bounded input, means input of a given amplitude and frequency, then the system should generate a bounded output. So I am giving a bounded output, say I am giving a bounded input, say a magnitude of 2 volt and 2 hertz, and the output goes tremendously high, 200 times, then we say that the system is going out of bound. So for the bounded input there should be bounded output. And the other condition is that as soon as you are eliminating the input from the system, it should gradually come down at its outputs. I should observe a decay of the output to a rest value or to an equilibrium position. So coming back to a stable equilibrium position if the input force is removed from the system is the second criteria for the system when the system is defined as the asymptotically stable system. So let us write it in statements. The condition one is that bounded output comes for every bounded input to the system, to the system. And the second condition is, condition 2 is, if input is, if input is made 0 at time t equals to 0, then output turns 0, output turns 0 for a time t1 greater than equal to 0, or reaches its equilibrium state at t1 greater than equal to 0, irrespective of the initial conditions. So these are the two conditions. If two conditions are satisfied, then the system will be defined as the asymptotically stable system. So these two conditions together define the asymptotic stability of a system. Then such a system model is said to have a bounded input, bounded output stability. So this is a very important and known concept in control systems. So let me write it down. Such a system model is said to have bounded input, bounded output stability, BIBO stability. So then we can say that stability of a system is defined with respect to certain parameters. So this is an important concept, bounded input, bounded output stability. And so with this knowledge, let us go further to define the absolute stability. So absolute stability. So as I mentioned, stability of a system is defined with respect to certain parameters of the system. So a system will be absolutely stable with respect to certain parameters we define for the system, because it can have many parameters, but we want to know that a system is stable for a certain set of parameters. If the system is stable for certain set of parameters, for whatever be the range of values of the parameters, then we say that the system is absolutely stable for these parameters. So I'm writing it down in words. A uh, system is said to be absolutely stable, absolutely stable with respect to a specific parameters of the system, parameters of the system, if it is, if or it can maintain stability for all possible parameters, for all possible parameter variations within practical range of interest. Practical range of interest. So that is not the case always. This is more about a theoretical idea. So what should be a practical idea about the stability of a system? Let us study that. So better keep it under the heading conditionally stable system. Or conditional stability. Under this heading, let us learn what is conditional stability, because in a practical situation a system can maintain stability for a bounded range of parameter variations as specified. Because if I am talking about a system which will work stably under certain conditions, let us say the example of a helicopter. We may have heard that a helicopter can fly in a very normal and suitable weather conditions. If it is heavy storm or heavy snowfall, under those conditions the helicopter cannot fly, because helicopter has a parameter variation range within tolerable limits for its controller to work perfectly. So whenever there is heavy wind or heavy snowfall, under those conditions the helicopter controller cannot overcome the flight limitations, which will bring the helicopter system to the verge of instability. So because of that, it is well defined for every control system. It is well defined that you can run this device within this range of parameter variation. Suppose you are using a computer or laptop, with the specifications they will define that the laptop will work perfectly within or up to 40 or 50 degrees Celsius of temperature. So such parameter boundaries are well defined for practical situations. So keeping that in mind, let me explain in words that a system is said to be conditionally stable if it can maintain stability, if it can maintain stability for a bounded range for a bounded range of parameter variation of as specified. So we can now say that a system model with all roots on the negative real axis of a plane will show asymptotic stability, as we studied in the case of asymptotic stability. So under which circumstances we can get the situation of asymptotic stability? So for that we can say that if we take a system and draw its S-plane roots, then you will see that if the poles are on the negative real axis, then the system will show asymptotic stability, means in time axis this output, the system output will decay like this whenever the input is removed, or it will show a stable output position like this. So if such a response is obtained from a control system, we say that the system is asymptotically stable, and we can state this as a system model with all roots on the negative real axis of S-plane will show asymptotic stability. So for other kind of roots, what are the situations? Let us investigate. Suppose you have all the roots on the negative real axis, as well as there are non-repeated roots on the j omega axis, then the system will be limitedly stable. So suppose I can write limitedly stable systems like this. So if we draw the root in such a way, then the roots are on the negative real axis, and there are certain non-repeated roots. So these are coupled. Actually, complex roots appear in complex conjugate form, so there are pairs. If this kind of roots are there, then the system will be limitedly stable, because in that case, suppose the time response we want to see, then suppose I am giving a step input to the system, so the response could be like this. Like this, because first the negative real axis roots will decay, and then the dominant roots, because these are the dominant roots, so this referred to these roots, because the dominant roots. These are the roots near the imaginary axis of S-plane. S-plane will last long. So if there are complex roots on the imaginary axis, definitely for that there will be sustained oscillation in the output after the steady state is reached, and this is a big challenge in control systems to cancel such root pairs or roots. So in case of limitedly stable systems, we can say that a system with all roots on the negative real axis along with non-repeated roots on j omega axis of S-plane, will be limitedly stable, So further we can see the systems which are unstable. So for unstable systems, you can write the heading unstable systems. So for unstable systems, which is more common during your experiment on simulations, if you are working on a real project, you will first see that whenever you are applying some controller, the system will become unstable. So by experience, while testing the systems, we experience more about the unstable systems, because initially the systems are not stable, and gradually by improving our design we can make the system stable. So what are the situations for unstable systems? We should know very carefully that if all the roots are on the negative real axis and one root is on the positive real axis, then the system will become unstable. So similarly, if all the roots are on the negative real axis and there is a repeated root on the imaginary axis, then also the system will become unstable. So in that case, suppose I am taking the example of these are the roots and this is the root, or another example of these are the roots and there is repeated root. So in that case, the system response time axis will definitely be, suppose I am giving a step input, so it will definitely be like this. So this is the example of unstable system. So a system with at least one positive real root, with at least one positive real root, or repeated roots, on the imaginary axis of S-plane will be unstable system. So there are situations when a system will have only non-repeated roots on the geometric axis of the spline, and such systems will be definitely called as marginally stable system. So let us take this on the heading marginally stable systems. We have the heading marginally stable systems. So how we'll see the marginally stable system? Let us see the spline where we have, suppose, non-repeated roots. If it is only one pair, you will see a system like this. Input is there, then there will be sustained oscillation throughout like this. If it is combination, then there can be the response will be different, and you can have for step input the responses can have a different set of frequency. So you can say that you can have a frequency like this, so that will be again sustained oscillation, but with some different frequency it will come. So such an example will be for the marginally stable system, when a system with only non-repeated roots on j omega axis of a spline is marginally stable. So this is some basic idea about the stability of a system. So if you have followed the lecture carefully, you should be making some idea about the stability of a system. So let us have a quiz to better understand that the concept is a little clear. Quiz. So an asymptotically stable system is R, or I can say will satisfy one or more of the following clauses. So number one is marginally stable. It means system, whether the system is marginally stable or not. Second, BIBO stable. Third is settles to 0 if input is removed, and fourth is all of this. So the answer to this quiz is hidden within this lecture. So if you have followed this lecture carefully, you can answer this, or you can retreat back to search for the answer to this quiz. So this much is for today, and in the Next lecture we shall discuss about the relative stability of control systems. So if you find this video useful, please like the video, and some of you have not subscribed the channel, please subscribe the channel if you are visiting for the first time, and set the bell icon for notifications, and stay in touch by watching the videos. And you can send any queries regarding the videos or control systems to my email ID controlsystemsfaq@gmail.com. So friends, thank you for your patient listening.